From a distance, the birth of a nuclear reactor begins as nothing more than a vast stretch of land. But beneath the surface, this site is about to transform into one of the most complex engineering structures ever created. Before any steel, concrete, or containment systems can rise, the ground itself must be reshaped, strengthened, and prepared to support decades of continuous operation. The first stage of construction is all about carving out the foundation that will hold the immense weight of the reactor and all of its safety systems. This is where the real work begins. Massive excavators descend on the site, removing thousands of tons of earth with precise, measured cuts. The soil is tested, compacted, and reinforced to ensure absolute stability. Surveying teams guide every movement, mapping the terrain with millimeter accuracy. As the ground opens, retaining walls and drainage systems are installed to control water flow and prevent settlement. The shape of the future containment building slowly begins to appear. Next, crews begin laying the reactor's base slab, a layered foundation built from high-strength concrete and dense steel reinforcement. The rebar grid stretches outward like a giant metallic web, designed to distribute forces evenly and anchor the structure during seismic events. Concrete mixers arrive in a continuous rotation, pouring an uninterrupted stream of material to avoid weak joints. Vibrators and leveling tools ensure the slab cures into a flawless, solid mass, one capable of supporting the enormous pressures of a functioning reactor. As the foundation cures, embedded conduits and anchor points are positioned for future systems that will rise in the stages ahead. By the end of this step, the once empty field has transformed into a carefully engineered platform, marking the first true milestone in bringing a nuclear reactor from concept to reality. With the foundation complete, construction moves upward into one of the most critical phases of the entire project, building the primary containment structure. This massive reinforced shell is the first physical barrier designed to isolate the reactor core from the outside world. Every inch of its construction is governed by strict engineering standards, as the structure must withstand extreme heat, pressure, seismic events, and even the improbable scenario of an internal explosion. This is where precision and durability take absolute priority. The work begins with the assembly of towering steel rebar cages, each piece carefully positioned to form the dense skeletal framework of the containment wall. These cages are arranged in circular segments, slowly outlining the unmistakable cylindrical shape that defines a nuclear reactor building. Cranes lift giant bundles of steel into place while crews interlock and tie each bar by hand, creating a grid so dense that it resembles a fortress before a single drop of concrete is poured. Once the reinforcement is complete, formwork panels are positioned around the rebar, forming molds that will shape the thick concrete walls. These molds must be flawless, any irregularity could lead to structural weaknesses. When everything is secured, concrete trucks begin delivering specially engineered high-strength mixtures. The pour happens in continuous phases, with long booms guiding the flow deep inside the forms. Vibrators eliminate air pockets, ensuring the concrete bonds uniformly around the steel frame. As the walls rise, embedded systems are added, pressure sensors, anchor plates, access channels, and future connection points for the reactor vessel and primary cooling loop. Layer by layer, the containment grows taller, its thickness sometimes exceeding a meter of solid composite material. The result is a structure built not just to support mechanical equipment, but to safeguard everything beyond its walls. At the heart of every nuclear reactor lies its most essential and heavily engineered component, the reactor pressure vessel. This immense steel cylinder is the chamber where nuclear fission takes place, and its strength determines the safety and stability of the entire power plant. The vessel must endure extreme temperature cycles, intense neutron radiation, and pressures that push the limits of modern metallurgy. Every stage of its creation reflects decades of engineering advancements and uncompromising safety standards. The process begins in specialized forges, where giant steel ingots, each weighing tens of tons, are heated until they glow bright orange. Massive hydraulic presses shape the ingots into thick-walled cylindrical sections. These pieces are heated, pressed, and quenched repeatedly to achieve the perfect grain structure, ensuring the metal will not deform or fracture under reactor conditions. After the forging process, expert welders join the sections using advanced automated welding systems capable of producing seams strong enough to behave as continuous metal. Once assembled, the vessel undergoes rigorous heat treatment inside enormous furnaces. This step relieves internal stresses and gives the steel its final mechanical properties. After cooling, precision machining begins. Robotic mills carve out openings for coolant nozzles, sensors, and control rod access points. Every cut is measured in fractions of a millimeter, with tolerances far tighter than those used in traditional heavy industry. After weeks or months of machining and inspection, the finished reactor vessel is transported to the plant site, often requiring specialized railcars, barges, or heavy-haul vehicles. There, workers prepare the containment building for one of the most delicate operations of the entire project, lowering the vessel into place. With the reactor vessel now secured inside the containment building, construction moves into one of the most intricate and technically demanding phases of the entire project, assembling the primary cooling loop. This system is the reactor's lifeline. It transfers heat from the core to the steam generators, powers the turbines, and ensures that the reactor remains stable under every operating condition. Every component, every weld, every valve, every length of piping, is engineered with absolute precision, because the integrity of this loop is critical to safe operation. The process begins with the steam generators, massive vertical heat exchangers often weighing hundreds of tons. Inside each generator, thousands of narrow tubes allow heat to flow without letting radioactive coolant escape. These units are built in specialized factories where robotic welders, X-ray inspections, and repeated pressure tests ensure each tube sheet is flawless. Once completed, the steam generators are transported to the construction site and carefully lifted into the containment structure, positioned opposite the reactor vessel. Next come the primary coolant pumps, colossal machines designed to push thousands of liters of superheated water through the reactor core every minute. These pumps are engineered to withstand extreme temperatures, radiation, and continuous operation for years at a time. Their housings, impellers, and seals undergo meticulous testing before installation. When the pumps arrive on site, they are aligned with laser-guided systems to ensure perfect connection with the primary piping network. The piping itself is unlike ordinary industrial pipe. Made from thick, corrosion-resistant alloy, often titanium-stabilized steel, it must endure high pressure and high temperature without failing. Workers assemble these enormous curved sections piece by piece inside the containment building. As the primary cooling loop reaches completion, attention turns to some of the most delicate and scientifically precise components in the entire nuclear system, the internal assemblies that govern the behavior of the reactor core. This includes the control rods, neutron moderators, instrumentation channels, and the intricate structures that hold the fuel assemblies in place. These parts are the unseen mechanisms that regulate fission, maintain stability, and ensure the reactor can be shut down safely at any moment. The process begins inside advanced manufacturing facilities where clean room conditions prevent contamination. Here, engineers fabricate the control rods, long, slender assemblies made from neutron-absorbing materials such as boron carbide or hafnium. Each rod is machined with extreme precision, allowing it to slide smoothly into and out of the core even under intense heat and radiation. Robotic arms handle the materials to avoid impurities, while automated welding systems seal the rod housings with perfect uniformity. Next, technicians create the core internals, guide tubes, spacer grids, and moderator components designed to shape the neutron flux inside the reactor. These parts must withstand high temperatures and corrosive coolant flow without deforming. They are crafted from specialized alloys and undergo repeated thermal cycling to simulate real operating conditions. After fabrication, every piece is inspected using laser metrology, ensuring exact alignment with the reactor vessel's internal structure. Once the components arrive on site, installation teams prepare the reactor vessel for one of its most intricate internal procedures. With the top head removed, cranes and precision tools lower the internal assemblies into place. Control rod drive mechanisms are installed above the vessel, connecting the rods to powerful actuators capable of inserting them instantly during an emergency shutdown. With the reactor core and primary systems nearing completion, construction expands beyond the containment structure into the massive complex that will ultimately convert nuclear heat into usable electrical power. This phase focuses on building the secondary systems, the turbine hall, generator infrastructure, condenser units, and the network of heat exchangers that transform thermal energy into mechanical and electrical output. While the reactor is the heart of the plant, this is the engine that delivers power to the grid. The turbine hall begins as a cavernous steel framework rising beside the containment building. Cranes lift prefabricated beams into position, forming the skeleton of one of the largest structures on the site. Reinforced concrete floors are poured with precision, embedding channels for steam lines, drainage systems, and vibration damping supports. As the building takes shape, specialized foundations are prepared to anchor the turbine assemblies, which must remain perfectly balanced during high-speed rotation. Meanwhile, in dedicated factories, the components of the steam turbine are machined with meticulous accuracy. Massive rotor shafts are carved from single pieces of high-strength steel, then polished until perfectly smooth. Blade assemblies, some small, some nearly as tall as a person, are precision engineered to extract maximum energy from the steam passing through them. Each blade is tested individually before being mounted onto the rotor, creating the complex multi-stage turbine that will spin at thousands of revolutions per minute. When the components arrive at the plant, installation proceeds carefully. Heavy haul vehicles transport the turbine casings and generator housings into the hull. Large overhead cranes position them onto their reinforced platforms. Technicians align the rotor within micrometers to ensure minimal friction and perfect balance. The moment construction reaches the systems phase, the plant shifts from heavy civil work to an arena of redundancy, control, and relentless verification. This stage is all about creating the layered defenses that ensure the reactor can be controlled under any conceivable circumstance. Teams install multiple, independent cooling circuits, primary, secondary, and emergency loops, each designed to operate autonomously if another fails. Redundant pumps, heat exchangers, and isolation valves are positioned so that flow paths can be rerouted within seconds, preserving core cooling even during extreme events. Parallel to hydraulic systems, technicians lay miles of industrial cabling and fiber optics. Trays and conduits snake through cable galleries, color-coded harnesses and labeled junctions make complex routing manageable. Every cable run serves a purpose: instrumentation, control actuation, safety interlocks, and high-voltage distribution. Electrical switchgear is mounted in reinforced rooms, where breakers, relays, and redundant power buses are tested and synchronized. Backup diesel generators and uninterruptible power supplies are installed in protected vaults, ready to sustain critical systems for extended periods. Control rooms are assembled like mission centers. Consoles, human-machine interfaces, and diagnostic screens are installed and networked to the plant's distributed control system. Engineers calibrate sensors that monitor temperature, pressure, neutron flux, and vibration. Data streams are routed through multiple channels to independent monitoring stations to eliminate single points of failure. Cybersecurity and physical isolation measures are integrated to protect the control logic from interference. Testing dominates this phase. Technicians run simulations that inject fault conditions into the control system, forcing automatic trips, valve actuations, and emergency cooling sequences. As the nuclear reactor approaches its first operational cycle, every system is pushed into a phase of intense monitoring and precise calibration. This final stage is the culmination of years of engineering, construction, and rigorous safety planning. The process begins with the initial startup sequence, where control rods are carefully withdrawn in measured increments. This allows the neutron population to slowly rise, awakening the reactor core for the very first time. Engineers observe every variable in real time: temperature gradients, pressure levels, coolant flow, neutron flux, and vibration signatures. Even the smallest anomaly can pause the entire process. As the reactor reaches its first sustained nuclear chain reaction, the facility enters low-power testing mode. Specialized instrumentation verifies that heat transfer is occurring exactly as predicted, that coolant systems are circulating flawlessly, and that the steam generation cycle behaves with absolute stability. Technicians perform thermal mapping of the reactor vessel, using sensors embedded during construction to detect even microscopic deviations in heat distribution. Once low power stability is confirmed, the reactor is gradually pushed toward higher output levels. Each power plateau includes a long series of evaluations, from turbine synchronization to electrical load balancing. Emergency shutdown systems are triggered intentionally to verify that the reactor can respond instantly under stress. Only after successfully passing these demanding trials can the plant enter full power mode. Finally, the reactor transitions into commercial operation, sending massive amounts of clean, continuous energy into the electrical grid. The once silent vessel now hums steadily, powered by a controlled nuclear reaction that will operate for decades.